Hello students and welcome. Today we are going to build a very strong foundation in coordination chemistry by learning some key definitions. You see, getting these terms right is the most important first step to mastering this chapter.
So I'm sure you have seen this in your chemistry lab, right? You take a light blue copper sulfate solution, you add some ammonia to it, and poof, it turns into this beautiful deep royal blue color. But have you ever stopped to wonder why? What is actually happening at the molecular level to cause such a dramatic change?
Well, to really understand that color change and to be able to describe these amazing compounds properly, we need to learn a special vocabulary. Think of it this way. Just like a doctor needs very specific terms to give a diagnosis, we chemists need a precise language to talk about coordination compounds without any confusion.
So, there's our plan. We will start by connecting that color change to the definitions. Then, we will explain the core vocabulary. After that, we'll use a fun analogy of a chef to make it all stick in your mind. We'll then visualize how these compounds form, and finally, we'll see how these definitions are used in the real world. All right, let's begin. We are going to start by understanding how the definitions we are about to learn are the key to unlocking the mystery of that color change we just talked about.
Let's dive right in. Imagine you are trying to build a complicated machine. What is the first thing you would need? A parts list, right? A list that tells you exactly what each component is called. Without it, you would be completely lost. Well, these terms are our essential parts list for building and understanding coordination compounds.
Now, for the most important part, let's unpack the four most fundamental terms in this chapter. Please pay close attention, because everything else that follows is built on these four basic ideas. First up, the ligand. So what is a ligand? It is any molecule or ion that has at least one lone pair of electrons, and it is ready to donate this pair. In this chemical relationship, the ligand is the giver. It's the one that donates the electron pair. So if the ligand is the giver, who is the acceptor? That is the central metal atom or ion. It sits right at the heart of the compound. You can imagine it has empty orbitals that are like open hands, ready to accept the electron pairs donated by the ligands. Everything in the compound is organized around the central atom. Next, a very, very important term, the coordination number. Now, this is simply the total number of bonds that the metal atom forms with the ligands. But here is the critical point, so listen carefully. We count the number of donor atoms that are directly attached, not the number of ligand molecules. I'll show you exactly why this is so important in just a minute.
And finally, we have denticity. This word comes from the Latin word for tooth. It tells us how many teeth a single ligand uses to bite onto or bind with the central metal. So a ligand with one tooth is called monodentate, one with two teeth is called bidentate, and so on. Simple, right? And this brings me to the most common mistake that I see students making year after year. They just count the number of ligand molecules they see in the formula. Please do not do that. You must always count the total number of donor atoms that are directly bonded to the metal. That is the correct coordination number.
Okay, I know these terms can feel a little bit abstract. So, to make them really easy to remember, let's use a simple analogy from everyday life.
Let's imagine a busy restaurant kitchen. The central metal atom is like the head chef, the boss, and everything in the kitchen revolves around them. The ligands are the sous chefs, or the assistants, helping the head chef. So what is the coordination number? It's simply the number of staff that the head chef is directly managing. A monodentate ligand is like a sous chef with one specific skill. And a bidentate ligand? That's a specialist chef who can handle two tasks at the same time.
So you might ask, why do we even need this special language? Well, the reason is to avoid confusion. In the early days of chemistry, different scientists would describe the same compound in different ways, which led to a lot of errors. This standard vocabulary ensures that we are all speaking the same chemical language clearly and without any mistakes.
Now that you have the chef analogy in mind, let's build a clear mental picture of how these ligands actually use their teeth to attach to the central metal atom.
Let's visualize this together, step by step. First, picture a central metal ion, let's say iron 2, as a target with a certain number of docking points. Next, a monodentate ligand, like ammonia, comes close. It has only one tooth, so it uses it to bite onto one docking point. Next, imagine a bidentate ligand, like ethylenediene, approaching. It acts like a pair of tweezers, using its two teeth to grab two docking points at once. This process continues until all the available docking points on the metal are filled and the complex is complete.
Okay, now that we have the theory and the visualization, let's apply our new vocabulary to some real-world examples. And I have one that might just surprise you.
Look at this complex ion. If I ask you what is the coordination number here, a lot of students would quickly say 3, but the correct answer is actually 6.
And this example perfectly illustrates the common mistake we talked about. In this formula, you see a 3 next to the N, which stands for ethylene diamine. So you might think the coordination number is 3, but that is wrong. Remember, ethylene diamine is a bidentate ligand. It has 2 teeth, or 2 donor atoms. So since there are 3 of these ligands, the total number of donor atoms is 3 times 2, which gives us a coordination number of 6. Is that clear?
Now you might be thinking, sir, this is all fine for my board exams, but does it matter otherwise? The answer is yes. Understanding these definitions, especially denticity, has massive real-world consequences. In the field of medicine, it can literally be the difference between life and death. Let me explain with something called chelation therapy. Imagine a person has lead poisoning, meaning there are toxic lead ions floating in their bloodstream. Doctors give them a drug called EDTA. Now, EDTA is a hexadentate ligand. It's a superligand with 6 teeth. This powerful ligand finds the toxic lead ion and wraps all its 6 teeth around it, forming a very stable, non-toxic complex. This complex can then be easily and safely flushed out of the body through urine. A ligand with just 1 or 2 teeth would not be strong enough to do this job.
So let's quickly recap the 3 most important things to remember. First, the core idea. Coordination number is always the count of donor atoms, not molecules. Second, the mental picture. Think of ligands having teeth that they use to bite onto the metal. And third, the real-world example. Remember how EDTA, a powerful ligand with 6 teeth, saves lives by removing lead from the body?
If you can just remember these 3 points, the core rule, the mental picture of teeth, and the EDTA example, I promise you, this entire topic will feel so much easier. You will be much more confident in your exams. You can definitely do this.
And to leave you with something to think about, we have talked about the number of teeth a ligand has. But is it possible that all teeth do not have the same biting strength? Could some ligands form much stronger bonds than others, even if they have the same number of teeth? We'll explore that question next time. Thank you for your attention.